I was sitting on some additional footage from my visit to Helion Energy, in which Dr. Kirtley goes into a bit more depth about some of the materials, construction methods, and Helion's approach to fusion. So I thought it could be valuable to share that with you here in its raw, unedited format and provide a bit of additional context for those of you who are interested in learning more. Now, if you enjoyed the video and you have not already done so, please subscribe to my channel. It's just me working on this channel. I worked pretty hard on that video, so it would really mean the world to me. Without further ado, here is Dr. Kirtley with some additional insights into Helion Energy.
So in this facility, we're building the parts for Polaris. So this is our test system for the fuel injector, for the plasma injector for Polaris. And so we're building this here where we'll test all of the gas injection systems, the initial heating, the ionization, and the making the field reverse configuration. It's a collection of very large diameter, for us, large diameter, pulsed electromagnetic coils. So as we're designing these electromagnetic systems, we have a team of engineers focused on how to build these. We make them out of advanced aluminum and advanced copper alloys that are very high strength and high temperature, as well as, and you can actually see it in the device behind me, that green insulator is G10. It's a special type of high temperature fiberglass, very strong fiberglass that's designed to actually hold those electromagnets. So in Helion's system, they're pulsed electromagnets, so not superconductors. We do have to cool them because they do heat as we run them, but our goal is to run them not cryogenic magnets, but our goal is to run them water cooled. So this is a pulsed capacitor assembly. So in this particular one, this is actually we're using for testing electrical insulation, so high voltage insulation. But in general, our systems work with a capacitor and a switch. So if you're used to electrical components, you'll know of a capacitor, which stores electricity very high efficiently. But typically a capacitor is about that big. This is a very high energy pulse capacitor where we charge up quite a bit of energy, kilojoules worth of energy, and then in a very short time, an electrical switch, which is in this coaxial can, switches and takes that electrical energy and takes it in less than 1,000th of a second and transfers it into these electrical wires. And so we have lots of high current electrical wires. These will go and hook into one of our magnet assemblies, and for this specific application, we're using it to test the electrical insulation. This thing is probably 1970s.
Oh, jeez.
And this has been used on has been as a test unit for all 7 of our previous, and in fact, this was used on some research and science programs even before that. And this capacitor, I think, has been being used since the 1970s.
Wow, it's longevity.
That's a lot, yeah. So one thing we found in our earliest systems is we could make these field reverse configuration plasmas, these FRCs, but the place where we made them, the formation chambers, ended up being very big and pretty complex with all the gas injection systems. So what we're currently doing is drilling using diamond drill bits. We're drilling windows so we can actually put more quartz, fuse more quartz windows in and use that to actually measure the fusion fuel as it's being injected and ionized in our 7th generation system. The divertor has a number of challenges. You have a materials challenge, because that is where your hot gas, whatever heat is remaining in your system now, is deposited within your divertor, just like in your exhaust system. The divertor gets hot. So we have to cool our divertor. We also use the divertor to extract gas, to pump any kind of remaining gas.
What kind of materials do you use in the divertor, which is taking so much punishment?
The divertor is where the exhaust for the fusion system goes. So we spent a lot of time designing this to be able to handle high heat loads, to be able to handle being under vacuum, and these may be complex gases like hydrogen, so you have some chemical reactions that may happen too. In a diverter, we use a variety of materials. Helion went and published a nice paper on this last year, talking about how you design a diverter for a magneto-inertial fusion system. Diverters will use high temperature materials. We use a combination of ceramics and also tungsten alloys that can handle some of these high heat fluxes that happen in a diverter.
What does non-ignition fusion mean?
So as you're compressing and heating a fusion fuel, fusion begins. And you can do a couple of things at that point. You can either keep compressing it until you get to a condition called ignition, where the fusion fuel now, as it forms energy, heats the rest of the fusion energy, the fusion fuel continuing to heat and continue to grow in the fusion reactions. The challenge with ignition is that there's some uncertain physics of what happens once you start to ignite the fusion fuel. So our goal is to compress and heat the fusion fuel until it begins to ignite and then turn it off. Expand it, get that electricity out of the system, put in new fuel, and repeat the process. Our goal in Polaris is to show that we can, for the first time, take a fusion fuel and heat it up to fusion conditions and then extract electricity from that fusion fuel. And so Polaris is not our commercial scale system yet. This is our can we prove that we can make electricity from fusion for the first time system. And so that's what we're off building right now. If everything works the way we hope, our goal is on the order of 2024 timeframe, we can actually show that we can make electricity from fusion for the first time. Yeah, I would say probably one of the biggest engineering challenges is what we call pulsed power. And doing that, building a large pulsed power system is something that Helion and our team of electrical engineers are world leaders in, is can you build large scale capacitor banks using, and this is really important, modern semiconductors, modern power electronics, to be able to take that large amount of pulsed power energy and turn that electrical current into electromagnets. And that's where we think fusion fits into that mix.
So can you tell me a little bit about some of the diagnostics you use in fusion power?
Yeah, so some of the most important things when we're building these fusion systems, these fusion fuels over 100 million degrees, is the diagnostics. How are you measuring what you're actually creating? How are you measuring how many fusion reactions you're making? So at Helion, we use a number of diagnostics on our fusion plasmas. We use magnetic diagnostics. They measure the magnetic field of the fusion plasma. They measure literally the pressure, how high a pressure is that fusion fuel. We also directly measure the emission, the optical emission of the ions, the electrons, all the fusion fuel particles. So we do what is called laser interferometry. That measures the density of the fusion fuel. We do X-ray spectroscopy. That measures the temperature of the electrons in the fusion fuel. We use a magnetic field, magnetic flux probes. Those measure the magnetic pressure of the fusion fuel. We also want to directly measure the fusion products themselves. And so we have neutron detectors that measure any neutrons that are made. We have alpha particle detectors that directly measure the fusion particles, the charged particles that come off the fusion reaction. And we have a team of scientists that do these measurements, that install the diagnostics, calibrate them at a variety of national labs, bring them back here to Helion, and then we run them and use them to measure how much fusion we're making and what our fusion plasmas are.
Excellent. What's that white building there behind you?
Yeah, behind me is the generator building. This is where we're going to actually install Polaris for the first time. And so we've been really excited to be able to build this building over the last 6 to 9 months here in Everett, Washington.
And how big is that building? Are there any specific attributes about it? Any safety attributes of note?
Yeah, in fusion, when we run fusion systems, for a variety of reasons, electrical and fusion reasons, we actually want to stay outside that building. And so in that, we actually will run the Polaris generator prototype, the earliest prototypes, from this building here, and it will be operated from across the street. And so that's about a 30,000 square foot building that'll have that for those first prototypes put in them.